Hi, welcome to Math with Marty. We're back again, and last week I got myself onto the topic of cubic equations, which I'm really interested in as it relates to the theory of solvability equations in general, in particular leading up to one of the most surprising and impressive results of all mathematics, the proof completed by Abel in 1831, based on the work of Galois, Gauss, Ruffini, Lagrange, Cardano, and Faro before them, and many others, proving that the fifth degree equation is unsolvable by radicals. And I'd like to get right into this, except I'm a little confused tonight because I came home last night. I've had a headache all day. I had a stomachache last night, and when I got home, my wife had this form of Chinese medicine that she put to work on me in order to make me feel better. And it involves taking a spoon and scraping it over the subject's back until red marks appear. Do you think the viewers would like to see what it looks like?
I think they'd be very interested.
Yeah. Well, okay, guys.
But I don't want to look.
It's not your back. It's something like this. Looks terrible, but it makes you feel a lot better. As soon as she stops doing it, it feels a lot better. My wife is Chinese, and when you say, well, it's not like you think of Connie Chung, you know, like I don't think sort of the westernized kind of Chinese Americans like Connie Chung is doing that to Maury Povich every night. But my wife sort of represents a more primitive branch of the Chinese family of peoples, and this is what we do. How do they say in the song? What goes on when the sun goes down? There it is. Now back to the third degree equation. I thought I'd set up an easy one for us that would solve without too much trouble, and I've decided to do x cubed plus x cubed equals 3x plus 4. And as I discussed last week, the idea of the solution is to try and guess what kind of form the solution should look like, based on the fact that solutions to the quadratic formula look like a plus the square root of b. We decided to try a more complicated formula for the third degree equation, and the simplest reasonable formula that might do the job was to take what we had and add a cube root of something, and then maybe add something more for good measure. And the problem with this formula is that based on the choice of the square root in this part of the expression, for the positive root, we get three values of the cube root, which we'll call p, omega times p, and omega squared times p, where omega is the cube root of unity, based on one choice of the square root. Based on the negative choice, you also get three values, namely q, omega times q, and omega squared times q. And it turns out, by the way, I've made it a little simpler on us. I don't have to worry about the extra constant c, because I've conveniently made sure that the original cubic equation I'm working on doesn't have an x squared term in it, which is real easy to do just by anyone in grade 11 math can accomplish that much. And what we got then is 6 values that this formula can assume. And we said, how could an equation which is supposed to have 3 solutions be solved by a formula which generates 6 values? The answer is incredible. The way this is handled is they take these in pairs. P plus Q, omega p plus omega squared q, and omega squared p plus omega q. So the solutions of the equation look like p plus q, omega p plus omega squared q, omega squared p plus omega q. And it is a difficult question how it comes to pass that we are able to unambiguously make the correct choice of these three pairs from among all the possible pairs that we might choose. But we'll get back to that later. We'll start by supposing that if we do find the formula to be of the form p plus q, that it's really not all that hard to solve the cubic equation. So I'll take some of this work off the board here. I'll just preserve our original statement that we are calling p, defining it as a plus square root of b to the 1/3, and q, it was being chosen a minus the square root of b to the 1/3. Now we'll just take this off the board. And all we got to do is assume that the solution of the equation is of the form p plus q. And we'll just write p plus q. See what happens when we cube it. Operating strictly by the binomial theorem, we get p cubed plus 3 p squared q plus 3 pq squared plus q cubed. Now I'm going to take this portion of it and take a common factor of 3pq out, which will give me p plus q cubed equals 3pq times, and from taking out the common factor of 3pq, I'm left with p plus q, and I'm left with still yet p cubed plus q cubed. And if we said that p plus q solves the equation, look what we've done. Look what we've done. We have p plus q, which if we said is going to be x cubed, then this is x cubed. We have p plus q here, and if we said in our original formula we want it to be 3x, we've got x cubed equals 3pq times x, plus what's left over, p cubed plus q cubed. So to solve the equation now, all we've got to establish is 3pq equals 3. That's the coefficient in front of the x. It's 3pq. So p times q equals 1. We'll write that down. pq equals 1. And what's left over at the end is the p cubed plus q cubed. And that had to equal the constant coefficient, which was 4 up to the top of the equation. So we have p cubed plus q cubed equals 4. Now to make it totally clear that this is solvable, I can cube everything. P cubed times q cubed is still 1 because cube is itself. And now I have an expression where I've got the product of two terms and the sum of two terms, which are both known to me in terms of integers, rational numbers. And this is solvable in a perfectly straightforward way as a quadratic equation. A quadratic equation is exactly an equation where you solve for two unknowns which are given in terms of their sum and their product. Rather than actually solving it, I will just point out that if we let p equal 2 plus the square root of 3 cube root, and q equal 2 minus the square root of 3 cube root, that p and q defined in this way do in fact satisfy these relationships. If I multiply them together, I get 2 squared take away root 3 squared, which is 4 take away 3, which is 1. Cube root of 1 is 1. And if I cube them and add them together, I get 2 plus root 3 plus 2 minus root 3, which equals 4, which is what I want it to be. So I've found, and this is just all that it is there is solving a quadratic equation to get these expressions. Once they've been reduced to this form, which is in the form of sums and products of two unknowns.
Okay, well that's fine, how you get the value for p and q, but what I want to be sure about here is you conjectured that the solution for x might have this form up on the right,
yeah.
But you didn't make any use of that. You just really, for the purposes of the way you filled up the board, you just said let the solution look like a sum, p plus q. So are you telling us that if you had decided that the solution for x could be the form p squared plus q, or pq rather than p plus q, or p over q, that it would have been impossible to get it to a form where you could sort of pick off the P and the Q by algebra? Like, all you've done is you've substituted P plus Q for X.
Yeah, okay. Now what
and then you've turned it into a form like the equation.
What you're telling me now is that I didn't have to assume the solution of this kind was going to show up at all. I could have just taken any old P plus Q.
No,
that's quite right.
That's not what I'm saying.
Except I think you're right if you're saying that. It looks like, I mean, I have barely, it's true what you're saying, I barely have explicitly used these conditions anywhere.
But we see the solution is of that form.
Except when we get down to the bottom, it does turn out to be that form.
I guess what I'm saying is the magic that comprises like the three main lines on the board, starting from P plus, the expansion of P plus Q cubed, is like by substituting P plus Q for X, you were able to get into a form that allows you to solve for P and Q.
Yeah.
Right? In terms of real
Since I get it in
numbers.
a form where I can solve for P and Q, why did I have to assume the form of P and Q to begin with?
Yeah, well, no, leaving
That's
aside the form of P.
Okay.
I'm not really talking about the form of P and the form of Q. I'm talking about the form of X. That the solution is of the form P plus Q.
Okay.
So I guess we're to understand that if you would have chosen, instead of using P plus Q like PQ or P over Q or something that was not P plus Q, that you would not have been able to get solutions like that. I guess that's, I'm just sort of trying to reiterate what you've sort of established.
Yeah, I think that it was necessary to assume the form was P plus Q in order to have this come out.
Well, that's one of the three combinations that you had on the previous board.
Yeah.
So you're telling us that only those three combinations will have something wonderful happen.
I think so. I think that's right.
Okay.
And having got to the bottom of the board and found that we've got the solution of the cubic equation, I think, why don't we pick up the guitars and do a song.
Oh.
Yeah, we got a special guest musician joining us tonight. He's a local man about town and well-known musician named James Meagher, and we've had some good times together and played a few songs in the past, and we're gonna see what we can get going tonight. Anyone you want to say hi to at home, James? Since you're on TV, have you ever been on TV before?
Yeah. America's Most Wanted.
Right. Well, say what you want to say before we start the song. You want to do that song that you wrote?
Okay.
I think we should do that one.
It's called Runaway Heart. Making all the same mistakes again. Couldn't hold my runaway heart. With every new lover I lose myself as my runaway heart fell under the stream. But in a while somebody else would come and steal away my runaway heart. And then my runaway heart ran straight to you. So fast I never saw it go. I was hanging around wondering what to do, while my heart was loving you so. And now my runaway heart doesn't stay anymore. Now that it found what it was looking for. All it took was your love so pure to capture my runaway heart.
Yeah, James.
Thanks, James.
That was
Good job.
That was real good. Some guys are endowed with the drive to create music. For me, I've never done much more than just want to be able to play songs I've heard, but...
It don't really much matter as long as you dig music. You know?
Well, it's all part of the same overall phenomenon, but...
That's right.
But how many songs did you say you've written in your distinguished career?
70 that I'll own up to, and a whole bunch that I flushed down the toilet.
Well, keep writing them, James.
Yep.
We're going to do a little more math, and then we'll return to the guitars for one more song at the end of the show. What have we accomplished here? On the board, we can see we started with the equation x cubed plus 3x, x cubed equals 3x plus 4. I did drop the microphone. Son of a gun. Son of a gun. We got the equation x cubed equals 3x plus 4, which we've broken down into sum of p's and q's, taken together in different ways. And we found that the expression is satisfied for particular values of these p and q, and we'll write them on the board a little bigger so that you can see them. Starting from this equation, I should rewrite the equation since I've drawn circles all around it. X cubed equals 3x plus 4. Starting with the equation, we said that if we take p equals 2 plus the square root of 3, cube root, and if we let q represent the same expression, except with the alternate choice of the square root, that we generate 6 actual values from these expressions based on the 3 choices of the cube root, which we'll call p, omega times p, and omega squared times p. Also q, omega q, and omega squared times q, where omega, of course, is representing the cube root of unity in the complex plane. And we said that from these 6 values, we can reduce these to 3 values by choosing these pairs, p plus q, omega p plus omega squared q, and omega squared p plus omega q.
I'm just wondering, did you say what were actually the possible combinations of taking those things?
Well,
I guess there's a very large number.
Yeah, you could have taken p plus omega q or p plus omega squared q.
Or all 3 p's and plus one of the q's. There'd be an enormous number of combinations.
Yeah, there is.
But there are other limitations, I guess.
Well, okay, it's easy to see that p's and q's are sort of different from each other because these p's are distinguished from each other as being multiples of a common factor. But having said you're going to take p plus q, you see, the whole thing about taking a cube root of something, when you take q as the cube root of 2, take away the square root of 3, how are you entitled to say which is the first cube root and which is the second cube root and which is the third cube root? Really, algebraically, they're all equally entitled to be called the primary cube root of 3. So if another guy had come along and written the same expression, except he had them rotated, so he had omega times q, omega squared times q, and q, his choice of cube roots is just as valid as my choice of cube roots, and yet by this formula, he would be expected to say p plus omega q is a solution of the equation, and he'd be wrong. And, you know, in a lot of the algebra books where they show this topic, they say the solutions are given in the form of p plus q, where judicious choice is made of the suitable cube roots. Well, what the heck do they mean by that? How can you just choose them right? There has to be a real way to choose them. And here's how it goes. It turns out that p times q, in this case, will be, let's multiply them out. We've got 2 plus root 3, 2 minus root 3. These are both to the cube root. So by the sums and difference of squares, we've got 2 squared take away 3, which is 4 take away 3 to the 1/3, which is cube root of 1. There are 3 values for the cube root of 1. There are 3 cube roots of 1. And while one of them is the ordinary number 1, and the others are these complex numbers off in the complex plane over here, omega and omega squared. So in this case, it is possible to distinguish one of them as being more special than the others. Whereas, supposing we'd started, instead of 2 plus the square root of 3, if we had started with 3 plus the square root of 2, we would have ended up with 3 plus root 2 times 3 minus root 2, both to the 1/3 power, which equals 9 take away 2 to the 1/3, which equals the cube root of 7. Now 7 does not have a rational cube root. So when you say the cube root of 7, you really are not allowed to say whether you're talking about the rational ones or the ones in the complex plane. They are really indistinguishable from each other. And the upshot of that is well, it's a funny thing. You can't make the choice in this.
Really, they strike me to be perfectly analogous, because one's sitting on the real number line, and the other two never live on the real number line.
Yeah, but the cube root of 1 is a rational number.
Okay,
and the cube root of 7 is an irrational number, and it's just as irrational as those imaginary ones, or complex ones, even though it doesn't live on the real number line. See, in algebra, in the purest sense, you're not really allowed to talk about where in the complex plane the number hangs its hat. You're only allowed to talk about its algebraic properties, whether it's rational, whether it's the square root of a rational, whether it's cube root of a rational number. And that makes the cube roots of 7 indistinguishable in a more profound sense than the cube roots of unity. Put it this way: whereas p plus q, with this choice of p's and q's, is the solution of a cubic equation in rational coefficients, if we took this kind of p and q, 3 plus root 2 and 3 minus root 2, we would find that p plus q, defined in this way, is not the solution of any rational equation of the 3rd degree. It's only the solution of a 9th degree equation, because there's 9 possible pairs you can take. This turns out to be a solution of some equation similar to x cubed plus cube root of 11 times x plus 5. It's an equation that would have 3 solutions, except since there's 3 cube roots of 11, that gives a factor of 3 on top of that again. So you get a solution with 9, you get an equation that should have 9 solutions. And so the trick is, when you're choosing the correct roots, you've got to choose them in pairs such that the pair that you choose to add together, if you'd have multiplied them together, you would have got something with 3 cube roots, only one of which is rational. Strange thing. I think we'll do a little more on this algebra topic when we come back next week. But for now, we've just about had it. I wonder if we got a song to end the show with. Got the guitars all fired up. Let's hear a little bit of a funny song about ants.
Oh, ants?
This is a weird song.
Ants. I dig ants. Look at them go! They move so quickly, ants. I like to watch them working, picking things up 20 times their size. Ants. Do you dig ants? They have antennae. They communicate. Ants. Are they not just amazing? I daisy. They work industriously, they're so small but oh so muscly.
James Meagher, how does he think of